So you're sitting in math class one day while your math teacher drones on and on about some new theory in mathematics called graph theory. You decide that this sounds like the simplest idea ever created, and instead choose to do something more productive like make paper airplanes. You start folding your second plane while the student next to you slumps over dead from absolute boredom. You're really starting to question what the purpose of this graph theory stuff is anyway. I mean, don't people make paper airplanes for a living? Well, not paper airplanes, but real airplanes. I think they're called aeronautical engineers or something. Okay, but maybe for real this graph theory stuff could apply to my paper airplanes. So I start to unfold my paper airplane and I notice, well, this looks kind of like an edge and this could be a vertex. But wait, if I'm going to do this, then I definitely need some rules and definitions.
On a flat piece of paper, you have 4 edges. We'll call them boundaries as special cases of edges. A fold is defined as going from boundary to boundary. This creates an edge between 2 boundaries. You must fold from boundary to boundary. You cannot create a half fold. At the end of this fold, there are vertices created at the boundaries. These have an odd degree. In this case, they are of degree 3. This is the case where the vertex is on the boundary. However, a vertex can also be created in another way, by 2 folds intersecting. When I make another fold, a vertex is created. This has an even degree, because I have to fold from boundary to boundary. This has degree 4. Folding through it another time still results in an even vertex. This arises from the definition of the fold. This now has degree 6. A series of folds can be continuous, but it doesn't have to be. You can fold, unfold, and fold again.
Now that I've established some rules and definitions, maybe I should try applying some of the concepts he is talking about. Colorability seems fun. If we only use the 4 edges of the paper, the graph is too colorable. But what happens if I start folding the paper? If we just use folds parallel to the boundaries of the paper, making rectangles, the graph stays too colorable. Within colorability, 2 vertices that are connected by an edge cannot be the same color. But what happens when we begin folding the paper into triangles? Will this mean that the graph cannot be colored with only 2 colors? Well, yes, the graph needs to be 3 colorable now because the 3 vertices are all connected. We have an open dot, a filled-in dot, and one with an X to represent the 3 different colors. We then made examples upon examples, all that were 3 colorable, leading us to the question, is it even possible to create a 4 colorable graph?
To that end, we should try to create a graph that isn't 3 colorable. We learned that wheels with an odd number of vertices on the exterior create 4 colorable graphs, as depicted here. However, this graph doesn't follow the definitions that we created earlier. The lines that I'm drawing in right now will help satisfy the definitions of folds that we created. I'll then number the vertices to show that there are now an even number, and therefore the graph is 3 colorable.
Now let's look at Euler circuits. I remember Euler circuits being defined as a graph with which all edges can be connected without using an edge more than once. To be an Euler circuit, all vertices must be of even degree. The graph shown here has all even vertices, and by tracing the edges, we can see that this is an Euler circuit. Now let me fold a random graph on this paper and see if all graphs created in the creases of our paper end up being an Euler circuit. Now I know that the interior vertices are all going to be even, so all I will have to do is worry about the exterior vertices. But this graph has 6 odd vertices on the exterior. Is there any way to make this graph an Euler circuit? Can we make every graph an Euler circuit?
In order to make every graph an Euler circuit, we need to make sure every vertex is even. In this first case, we have 4 odd vertices, 2 on each boundary, and connected to all but every other vertex. In order to make these vertices even, we can simply fold between the odd vertices that are not already connected. Now each of the 4 boundaries are even, with degree 4. In this next case, we have 2 odd vertices that are already connected by a boundary. To make these vertices even, we create a vertex on a different boundary and fold both of the vertices to that one vertex. This prevents us from creating a new odd vertex and makes both of the other vertices even. In this last example, we combine these 2 concepts. This example has 4 odd vertices, In order to make these vertices even, choose any two that are not already connected and create a fold between them. Now both of these are even. There are two remaining odd vertices that are already connected, so you must create a new vertex to connect both of these odd vertices to, with two folds. Now, all of the vertices on the boundaries are even. Even the interior vertices are even by the definition of a fold, and we can now create an Euler circuit.
Now let me apply the algorithm to one of our more complex three-colorable graphs. All of these vertices are degree 3, so they must be changed in order to make this graph an Euler circuit. By the algorithm, I will connect the odd vertices to make them even. Now I will draw the edges, but this ends up ruining our hypothesis on three-colorability.
But now we've ruined our hypothesis of 3-colorability. We now have a 4-colorable graph. What does this mean? Can there be 5-colorable, 6-colorable? I don't even know. And I didn't even talk about Hamilton cycles. Maybe that's what I'll do next. Oh, it looks like the teacher might actually be paying attention to me this time. I better get rid of this stuff right now.